Alright, everybody, get started. So, plan for today. The next thing we're going to do on this course is quaternion rotation sequences, and we'll start them today, okay? If we get time. But just before we do quaternion rotation sequences, I think we've kind of reached a bit of a milestone now that we can actually generate world transformation matrices, and you understand hopefully a little bit about how 3D graphics work. So I think it's just a nice time to maybe just take a pause and just consolidate our existing knowledge and say, like, what do we need to know at this stage? And also, I think the lab actually this week was a really sort of a very important lab, because you kind of have all the vector stuff, and now you're making a world transform matrix and you're drawing something. Okay, you're missing how to do the rotations correctly, which is the quaternion rotation sequences. But I want to just make sure that we're sort of square on particularly how to make the world transform, what it means, matrices, vectors, rendering, all that kind of stuff. Another thing about the lab, don't worry if you couldn't complete it, alright, particularly the second part. What tends to happen with me sometimes is I start writing things, like I did the first part of the lab, and then I thought, well, I better put another bit on, because that won't take too long for people to understand it. And then I started doing this little particle thing, and I just got really carried away. And that's what happens when you start writing games, like things like that, and particularly when you start making things which are procedural, like those little fountain effects. It's very addictive, and you just can't stop yourself, right? So I even made a thing today, which just, you know, in terms of the assignment, it's something that we can try out on the Rift and see does it work or not. Just using particle effects in one 3D model. I only hacked it together in about an hour or so. It's not too fancy, but just in terms of what we can do for the assignment. So that's the plan. The next big thing that we're going to talk about is quaternion rotation sequences. But before that, just the other thing with regard to the lab. I was very impressed when I walked around to see people like thinking like programmers. You know, it wasn't like, oh, I don't have a clue how that's done. People were actually sitting there and working it out. And I suppose hopefully now you're realizing that, you know, there's two skills you're going to learn as programmers. You're going to learn the syntax of the language and what APIs to call and the rest of it. And then the other aspect of being a programmer, which is 50% of the job, is the thinking bit, right? And the thinking bit you're learning on this course is a thing called analytical geometry. So you're hopefully learning how to position things in 3D space and be able to think in your head, okay, this is the angle I need to calculate, or this is the distance, or whatever. And most impressive for me is when I go around and I see people and it doesn't work for them, and then I say, oh yeah, you need to do the exterior angle, interior angle. They go, oh, okay, that's what it is. So people are totally getting it, and that's, for me as a lecturer, it's very gratifying when people are kind of reaching that stage of being able to comprehend a reasonably complicated thing very quickly like that. It's impressive, right? So that's what I wanted to say. So just in terms of the lab, right, and just in terms of where we are at the moment. So last week we were talking about matrices, and just very quickly we discovered that in terms of graphics programming there are 3 different types of matrices that we can program to achieve various different effects. What are the matrices we can make? Yep, so we can make matrices that translate, that rotate around various different axes, and that scale. And we combine translation, rotation, and scaling matrices typically to make something called, you know this from the lab, which type of transform is it we make? You know, in order to draw a model in a scene, what do we make? Well, what did you guys set in the lab, do you remember? It's called the world or the model transform. Alright, so you translate and rotate. You translate based on the objects. What determines the translation matrix? The objects. You know this. The objects, position. So you use the x, y, and z of the position to make a translation matrix. The rotation, has anyone figured this out yet? What do you use to represent the rotation? What makes the rotation matrix? You can just make one from a scalar if you want to do very simple rotations. We haven't done it yet. The rotation matrix is made from the object's quaternion. Are you intrigued about the quaternion? It's there. It's just like a little bit of magic that we haven't even scratched, you know, yet. And then the scaling. What do we make the scale out of? Just, you know, thinking about it. what do you need to make a scaling matrix? You need how many numbers? 4, 3, 5. Yes, 3. You need 3 numbers. So we're going to make this from a 3D. What are we going to make it from? 3D. Go on, not a 3D matrix. There's no such thing. 3D. You know it. A vector. Okay. So all objects in BGE extend this base class called game component, and they all have a quaternion, a vector which determines the scale, and another vector which determines the position. These generate different matrices which are then combined together to make the world matrix. We need 2 other matrices in order to draw a thing. What are they called? These are really important, by the way. You might remember from the class last week.
Identity matrix?
The identity matrix is just a matrix. It's sort of somewhat useful in the generation of other matrices, but not essential for drawing something. If you want to draw something in 3D, you need to give it 3 matrices. You give it a world matrix. What's the other thing you give it? What's the thing that determines the camera position called? That matrix is called, can you remember? I probably flew through this last week way too quickly. You need another matrix, and it's called the... Oh, I definitely said this last week. It's called the view matrix. Alright? So looking at the step, we take our object in local space, we multiply it by what we call a world or a model transform, depending on which book you read. And then all of that stuff gets multiplied by the view matrix. What does the view matrix do? It kind of does 2 things. Where is the camera in what's called view space? So, we set up our scene, right? I'm going to draw my cube over here. I've got an eye looking at it down here. Of course, it's going to look differently depending on what the camera's position is. If the camera's there, it's going to look one way. If the camera's there, or the eye is there, you're going to get a completely different representation of your 3D object, obviously. So the view transform, where is the camera in what's called view space? What does it do? It rotates everything relative to the... Have a guess. Don't worry if it's not the right answer. Huh? Yeah, go on, have a guess. Try it out. Huh? Rotates and translates everything relative to the camera. So in what's called view space, the camera is located at position 0, 0, 0. And in OpenGL, the look vector for the camera in view space is always the vector 0, 0, and -1. So the camera looks down the negative z axis, and everything is translated and rotated relative to the camera by the view transform. That's what the view transform does. So for example, if my object was located at position 5, 5, 5, and my camera was located at position 6, 6, 6, my camera goes to position 6, 6, 6. My camera goes to position what? 0, 0, 0, and everything gets moved to... What's this going to be? It'll be -1, -1, -1, won't it? So in this example here, I subtract 6, 6, 6 from the camera, it becomes 0, 0, 0. Subtract 6, 6, 6 from this, and it becomes -1, -1, -1. So everything stays in the same relative position, but the camera moves to the origin, and everything moves by the same amount. We could take a very simple example of how the camera rotation might work, right? That's... I won't do a maths example because I might actually screw it up, right? But what you have to imagine is that my camera is looking at everything. Say here's my camera somewhere in the scene, my camera is looking at this object here. What happens is the camera ends up looking down the negative z axis, and the object rotates like this. So that the camera is still looking at it. The camera position and orientation relatively are the same, but the camera is moved to 0, 0, 0, and everything is rotated so that it's still, in the relative position of the camera. Does everybody understand that? Now, I'm going to show you some code, like this, it's not just theoretical, you actually have to program all of this stuff. So that's the view transform. Can anybody remember how you make a view transform matrix, or did I even mention this last week? There's an API call in GLM for making the view transform matrix. We'll look at it.
It's not perspective, is it?
No, that's the other one, right? That's the third one that we need to do, called the model view and the, what's the third one called? Projection, yeah? So, we have this view matrix. Does anybody know how you make one of these? There's an API, the GLM has an API call for making one of these matrices. Anybody know what it is? If you don't know, I can't remember if I mentioned it or not. It's GLM : look at. So this will make a view transformation matrix for you, and it takes a certain number of parameters, which I'll show you in code in a minute what the parameters for the look at matrix. That makes the view transformation matrix. So, we take our geometry, multiply it by the world transform matrix. Next thing, we multiply it by the view transform matrix. And that's got our position and everything relative to the camera. We've got a third matrix which is required for 3D graphics. And that, did I start the camera? Is there a red light on it?
Yep.
Cool, alright. The third one is called the projection. The projection matrix. And what's the purpose of the projection matrix? You got it. Okay, so what it does two things. First of all, it does lots of things, but essentially what it's going to do is it's going to take all of this 3D stuff and make a 2D projection of it. Okay. The other thing that it does when that 2D projection takes place is that it applies, I think the term is called foreshortening. I think the term is called foreshortening. Maybe somebody could Google that word and let me know if that's the correct term. But what it basically means is far away objects become smaller and near objects become bigger. So it scales everything based on the distance of the camera. I was just thinking of that Father Ted sketch. You know that one? Okay. So, I should really have put that on my slides. That's going on the slides for next year. So that's what the projection method. There's another one. No, but there's a very, very amusing moment, yeah, when he does the model. Okay. Somebody find it over there, will you? You know the scene I'm talking about? That's right. Alright, that's the one, yeah. So that's what the projection matrix does. It makes faraway objects smaller and near objects. So it scales everything based on distance of the camera. And also it takes your 3D image and it makes a 2D projection out of it onto a plane. So I happen to know what the parameters for this are because they're just interesting parameters. So what do you think, or can you guys remember what the parameters to this API call is? What would you need to tell it?
Field of view.
Huh? The field of view is one thing. Okay, so the field of view to generate. Something else that you give it is called the near clip plane and the far clip plane. And what those parameters do is they tell OpenGL basically to not render things beyond a certain distance or closer than a certain distance. So it's like an optimization thing. And that's called the near clip plane and the far clip plane. So when you're setting up to do 3D graphics rendering, it doesn't matter what you're using. It doesn't matter even if you're using Unity or you're using OpenGL or you're using Ogre. Ultimately, when you're programming 3D graphics, you set up these three matrices. You pass these three matrices along with all the vertices you want to render to the graphics card. The graphics card then goes and assembles the, it's called the frame buffer. So it goes and assembles what appears on the screen. All of this basically goes to the frame buffer. Now, something you mightn't know is that in the old days of OpenGL and DirectX programming, even when I wrote this course, all of this you basically wrote as C API calls. But a certain amount of this now, in fact, this actual multiplication bit is actually done on the graphic card in a program. And those programs that run on the graphics cards are called shaders. So you'll notice in BGE when I load it up that there's a folder called content and it contains loads and loads of shader programming to do different things. And the shaders are written in a language called, I'm not going to get into this in too much detail, we'll actually come back to it towards the end of the course if we have time. It's more of a graphicsy kind of thing rather than a game specific thing, but they're written in a language called GLSL. And GLSL is based on a language which you all did many years ago called C. So it's based on C. It's not an OO language. And when you look at GLSL code, you'll see, yeah, there's a main function, and there's some variables declared, and there's some multiplication stuff. Some of the shaders are really easy to understand, some of the shaders are more complicated. Specifically, in BGE, and in a lot of fairly simple kind of graphics programs, we use two types of shaders. We use one type of shader which is called a vertex shader. I'm just going to write these up, and this is as much as we're going to do on shaders for now. I'd love to spend maybe a class or two talking about how lighting, the standard lighting model works, but we'll do it towards the end of the class if we've got time. That's not on your exam, so I've written your exam. So we write these things called vertex shaders. And the other type of shader we write is called a fragment, or a pixel shader if you're doing DirectX. Fragment. So the purpose of the vertex shader is to do this multiplication job. You pass in the vertices you want to render, you pass in the three matrices, the vertex shader goes and does the multiplication operation for every vertex, and it outputs the vertex in screening space. The fragment shader then says what color do you want that pixel to be. So there's the two little programs that get run on the GPU. And I'll just show you them. I mean, we're not going to spend a lot of time on these, but we'll maybe come back to them towards the end of the course, right? But that's in a nutshell, that's how graphics works. That's how 3D graphics works, right? I have written notes on all of this, by the way. It's all in PowerPoint slide number 3. I'm working on notes version number 4, which explain all this stuff in a little bit more detail as well. Let's take a look at the code that does all of this for the hell of it. Just, you know, to prove that I'm not just making all this stuff. But we won't, like I say, we'll come back to this later on in the course. I'm going to show you a class in BGE, and it's called a model class. And the model class essentially encapsulates all the vertices and all of the colors and things for a 3D model. So I'll just show you very quickly how all of this stuff gets passed to the GPU, and we won't talk about it really in a lot of detail, and this isn't really coming up on your exam to any huge extent, but it's just interesting to observe. So I have a vector here of vertices, I have a vector of normals, which are used to calculate lighting, and I have a vector of UVs, which are used to say what part of what vertex is mapped to a particular texture. That's what a UV is called. And then colors. But again, we'll come back to this later in the course. It's actually very interesting. Okay, so if you want to look down here at the draw method for this thing, this is the draw method. So let's say the model is textured, right? Without getting into too much details, there's no point in really talking about that, but here's the interesting bit down here. First of all, I pass those three buffers to the vertex shader. And so this line of code here, GL get uniform location, this basically binds a vertex buffer, a vertex shader variable to a C++ variable. So that basically says there's a vertex shader variable called M, and I want to refer to it in my C++ program as MID. So this is how you bind from C++ code to GLSL code, right? So then model, look at that, there's the model view, the projection. There's another matrix we pass in called the normal matrix, which I'll explain maybe later in the course. The normal matrix is used to rotate normals. You can't transform them by the world transform, otherwise they will end up changing the position of the normals, and you don't want that. Also, I'm passing in like ambient specular and diffuse lighting. And so I bind all of these things here. Where is this? That's on my initialize. And then looking at the draw method down here. So at some point, I'm going to copy all of that information into those buffers on the graphics card. And I bind these things to variables on the, this is me actually saying, okay, take this vertex buffer and copy it into the GPU. Take the normal buffer, and let me just show you where the uniform, this is me passing in, when you do GL uniform, this is me essentially passing in variables into the shader programs. And you'll notice, yep, here we go. This is the most important code here. Assuming that there's some code to copy all those buffers into the shaders, here's some code which basically takes the three matrices and passes them into the shader, which is necessary for the thing to get drawn. So first of all, here's me passing in the world. So this is basically the world member variable. This thing here is the member variable called view in the camera class. So So I take the view from the camera class and I pass it into the shader. And here we go, I take the projection from the camera class and I pass it into the shader there. So every time I draw something, I take these three variables from BGE and I pass them into the shader. The shader then goes and renders the vertex buffer, making use of those three arrays, making use of those three matrices. Let's have a look at the camera.cpp file. In the camera CPP file, the perspective matrix, I only need to make it once. It never changes. The camera position is irrelevant to the perspective matrix, right? But here's me making the perspective matrix. First parameter, this one, can you remember, this is the field of view. Second parameter, 4/3 is the aspect ratio. This is terrible. I should get this from the screen width and the screen height. Surprised, I will definitely make this change and commit it to the if thing. And this number here is called the far clip plane, the near clip plane, and this is the. We'll try modifying these so we can see what effect they have. So that's me making this matrix. So this is the call that you use. It's called a perspective. The other one that you can make is an orthographic. Can anyone tell me what an orthographic projection is? If anyone's doing any OpenGL stuff.
Distance doesn't matter, I think.
Distance doesn't matter. It doesn't do the scaling thing based on the distance. Everything is the same size. Why would you use an orthographic projection?
Or something like a map or 2D text.
2D. So you can use an orthographic projection to draw stuff in 2D. It means it doesn't matter. The Z then is going to indicate what gets drawn on top of other things, but it basically draws everything the same size. So that's an orthographic projection. And GLM code orthographic sets one of those up. So that's me making the perspective projection. Yep, here's me making the view projection. So I go view, the view field equals GLM look at. So you pass in the position, the look vector, and the up vector. And then it generates this look at vector, which is the view matrix. That's how you make the view matrix. And we already figured out, or you would have figured out from the lab, you make the, look at gain component here. You basically make the world transform. If you look at this here, you make the world transform for every object in the scene by just combining the translation, the orientation, which is, and we'll talk about this maybe later, or next class, whatever, and then you also multiply by the scale. So, interestingly there, what happens first? The translation, rotation, and scale. Which happens first? Scaling happens first, because they're done in the opposite order. So the scaling, then I rotate it, and then I translate it. So you can switch the order. That's me calculating the world transform. All of those three things get passed into a shader. I'll show you an example of a really simple shader. Because if you look at the shader used to draw those 3D models, it has quite a lot of really nice things to calculate ambient, specular, and diffuse lighting. So I'll just show you a really simple shader. We'll just look at triangle shader. This is a vertex shader. Cool. This is really simple vertex shader. Can you see that code there? I'll move it over a little bit. Yeah, we're missing a bit there, but basically this is what a vertex shader looks like. First line in the vertex shader, have a guess what this does. Sets the version of OpenGL required to run this shader. So if your OpenGL does not support OpenGL 3.3 core, then this shader won't compile. Interestingly, can anyone tell me or have a guess of when are shaders compiled? These shaders, right, you can see that they're in a C-like language. Eventually this has to be compiled into GPU instructions. Same as if you're writing a C program, eventually it gets compiled into assembly language, right? When does this get compiled into GPU instructions? Even when you're running any 3D game. Is it built into the exe? Is it pre-compiled? Have a guess. Huh? It's not, no. Interestingly, you ship the shaders with your program. Or you compile the source of the shaders into your program. And then when you go to want to render something in 3D, this gets compiled at runtime. It gets compiled at runtime. It's possible you can ship a shader which doesn't actually compile. Your thing doesn't work. Interestingly, I'll show you what happens when you have code in your shader that doesn't compile. The thing will still render, but it's going to look terrible because it won't do anything with the shader.
Is it read interpreted then rather than compile?
No, it's actually compiled, but it's compiled once at runtime. And it's the OpenGL driver that compiles it. And this might get compiled differently on the NVIDIA GPU versus an AMD GPU or an Intel GPU. So it compiles it into different instructions depending on the GPU. But if they support the OpenGL standard, then they have to interpret this the same regardless of what the GPU is. Okay, have a look at this. In Vec3, vertex position model space. What do you think that means?
Would that be the input?
Yep. And it's a vector 3, so it's the position in model spaces. Okay, there's better ways to do this, and some of the other shaders do it a little bit better. This is me passing in the MVP matrix. This isn't a great one. Most of my shaders, I actually pass these in separately, and I multiply them in here. But this is the MVP matrix. Again, what order is this? You know, it's written MVP, but imagine I've made it in that order. That means I do the projection, the view, and then the model. And I think that's the way you're meant to assemble them. So you assemble them in that order. And you can see here I make this Vec4, which just takes the vertex position, adds a 1 to the end of it to make a 4D vector out of it, because we need a 4D vector. Why do we need a 4D vector? Yeah, because it's a 4x4 matrix, so I have to add something to the end of the vector. And then I just take the MVP and multiply it. This is a shader which is actually doing that thing. You know, it's taking the vertex and it's multiplying it by the MVP matrix. So it's going to output it in screen space. And then it gets passed into the fragment shader. There you go, that's a really simple fragment shader. It doesn't do anything really. All it does is it sets the color of the pixel or the fragment. That's a fragment shader. Like it's, you know, it's a really pathetic one. You know, it doesn't do anything useful at all. The color is even hard coded. You can pass these in and stuff. You know, but it's just to show you how 3D graphics essentially work. You know, you set up those 3 matrices, pass in a load of vertices, run 2 programs on the GPU. One called a vertex shader, and one called a fragment shader, and you get your pixels at the other end. Cool. Happy? Alright, so that's how 3D graphics works. In terms of BGE, you can write all your stuff in C, but in terms of BGE, I like to, well, let's not do this. Let's do the solution to the lab first, right? How many people finished the first part of the lab? Excellent. How many people finished the second part of the lab? Good stuff. How many people knew or had a clue or were doing something along the lines or had a strategy for the second part of the lab? Alright, so the second part of the lab is actually easier than, you know, it's just sine and cosine. And if you remember back to the unit circle, that's all we did to do the second part of the lab. I'll just show you the code. Okay, so there's a couple of interesting things here. I don't know if you guys remembered, but when we were talking about sort of BGE, and this applies not just to BGE, but all game engines, we talked about there being an initialize, like SE, update, draw, and cleanup. And this bit here is called the game loop. So this executes over and over again. You calculate the time delta and you pass this bit in here, okay? Interestingly, one of the things that BGE does is it has this idea of components, which is, I didn't make this up either, this is what Unity does in most game engines. Each component can have a list of children components. Each child component have its own set of children components. And that way you end up with a tree of different sort of component things, right? But one of the things that happens when you go game : update is that every object has its world transform calculated based on its position and based on its quaternion and its scale. So what are we doing here? The reason why this code goes after this code, what am I doing here essentially? I've already calculated the world transform for everything that's attached to the game. So what am I doing here? Sorry. What am I doing here? Have a guess. I've already calculated a world transform for we're looking at shift 1. This has already been calculated. So what am I doing here? I am overwriting it. I'm overwriting the value that's calculated from its position and its quaternion. So, this is what's going to get passed into the shader, not the one that I've calculated up here. That's why I put this code after the update method, which is not the normal way to do it. Normally you let the engine take care of it. You set its position and quaternion. The engine takes care of calculating the world transform. But we're calculating it manually here, just so you can get the idea of how to calculate world transform matrices. So anyway, yeah, the code, simply enough, calculate the 2 shift 2 vector. It's going to be shift 2 position minus shift 2 1 position. Shift 2, I normalize it, and then I calculate the theta value as being the dot product between the basis and the 2 shift 2 vector. So what's going on here? 2 shift 2 dot x is greater than 0, theta equals minus theta. Those of you that completed it. Why am I doing that? Yep, why do I need to calculate that? And why is it that if shift 2x is greater than 0? Sorry, the 2 shift 2x, what exactly is happening there? Absolutely, yeah. So first question then. What way are the rotations being applied? Counterclockwise, okay? So if you draw your little scenario here, top down, that being the negative z-axis, that being the x-axis. If that's shift 1, that's shift 2 there. If I go and calculate this angle here, and I apply this rotation to this ship, the ship is going to rotate in this direction. Isn't that the case? So what I'm doing here is I'm checking to see if I'm on this side of this ship, then instead of doing my rotation counterclockwise, I want to do my rotation clockwise, to negative the theta value. An alternative way to do that is to say there's the theta that I've calculated, and just take the exterior angle. How do you calculate the exterior angle? Yeah, 2 pi minus the angle that you've calculated. So that's 2 pi in total. That's theta. If you take 2 pi minus theta, you end up getting the exterior angle like that. So that's why. Does everybody understand that 100%? Is there any questions on that? Now is the time to ask. I mean, really seriously.
What is getting the external better?
Well, I'll show you. In fact, it's probably better if we actually run it and you'll see straight away what happens, right? So say I just calculate theta. I'm going to comment this code out, right? I'll run this thing. Okay, it might take a little while to build. Hope this is the right for it. Let me just my main method. I'm going to spoil my beautiful demo for the Rift. Yeah, that's the Rift thing. Never mind. Back to that. I just need to change this to the sprint lab, do lab 5 instead, right? It's quite easy. If you see it from above, and then once you get this, your head into this, like it's, you'll have a very good understanding of how rotations work. Alrighty, I'll modify my code very slightly. Okay, look at that straight away. Never mind about the particle effects and stuff like that. But what can we see? This thing is fine. This thing is okay, doing its do. This thing's pointing in the wrong direction. And if you need to move this guy or this one, if you move this guy, you see it's always going to point in the wrong direction. Can everybody see that? Until I move this guy over here, and then suddenly it starts pointing in the right direction. And then when I go over this side again, it's suddenly going in the wrong direction. Does everybody see that? Okay, so looking at it from above, what's happening here is this ship, that's its basis vector, and I want to apply a rotation to that guy. This is the other ship over here moving around. What I do is I end up calculating this value here. That's the theta that gets calculated. But because the rotations are counterclockwise, when I apply that rotation, the rotations are going in this direction. Because that's what it is. If I say rotate theta to radians, it's going to rotate this way instead of this way. So I need to then decide, okay, if I'm rotating in the wrong direction, this guy's over here, I need to say if this guy's on this side of this guy, then I need to rotate in the opposite direction. So I take minus rotation, and that's going to rotate in the opposite direction. Or alternatively, you get the exterior angle. So you take Because if you look at this, if I was to calculate theta in this way, there's these two guys, that's A, that's B. A rotation of theta radians this way is the same as a rotation of 2 pi minus theta radians in the opposite direction. So I can rotate theta radians this way, or I can rotate all the way around to here, which is 2 pi minus theta, so that's in the opposite direction. Everybody happy with that? So you now know how to calculate rotations in 2D. Is everybody 100% happy with that? You sure? Cool. Alright, let's do the second part. The second part was just really a bit of fun, and I gave you some sample code to generate a fountain. So just looking, okay, say I want to set the initial positions for all those fountains around the outside. You could do it the hard way. And the way, say, a lot of people who've done games jams but don't really know anything about programming might do it would be to say, okay, I'll make a guess at the points around the outside there and I'll position things until they look right, and spend quite a long time looking at it and trial and error until it gets right. A better way is to write some sort of a function to calculate those points on the outside of a circle. So, how do we calculate points on the outside of a circle? Huh? Yeah, well, look at, let's again make it, you know, draw our little unit circle like that, draw a circle like this, we'll put this roughly in the middle here. So first of all, we'll say that there's maybe 10 things around the outside. If there's 10 things around the outside, then I want theta to go all the way around the outside in 10 steps. So how do I calculate theta? 2 theta over 10.
2 pi over 10.
Sorry, yeah, maybe, yeah, that's perfect. Yeah, so I'm going to just take 2 pi divided by the number of steps. And then that gives me what interval to use, right? Equally, so that's the thing, that's the first bit. If I was to write a for loop, then I can just take the index of the for loop multiplied by theta to calculate theta. And the for loop goes from 0 as far as 20 steps around the outside. You're very happy with that? Yeah, cool. So now I can calculate theta. What I then need to do is calculate the x, and in this case it's the z coordinate, right? For these points on the outside of the circle. So, I mean, let's just make a right angle triangle. In this case, what's our radius? We're given a radius, right? We're given a radius, and I think I said the radius is equal to 40, isn't it? So then if I draw a line across there, I discover that this becomes a right angle triangle, doesn't it? And then the challenge is calculating x and y. Well, we know from the unit circle that x, in this case, we can say that the sine of x is going to be equal to the opposite. The sine of theta is equal to the opposite, which is, the opposite in this case is x, isn't it? Can everybody see that the opposite of this little right angle triangle is x? Can you see that, everybody? It's just a unit circle. X divided by the hypotenuse, which is 40. Well, we're given theta, and I need to calculate x. So we just multiply both sides. So you end up with sine theta multiplied by 40 is equal to x. And that's how you calculate the x position. See that? So you kind of already knew it. It's just maybe a matter of applying this in a slightly different way. So then the next thing I want to do is calculate y. And what can we say about y? Y is the, looking at the cosine ratio. The cosine ratio is the distance from here to here is going to be y. So I can say that the cosine of theta is equals to the y value. So the y is the distance there because it's the adjacent over the hypotenuse, which is 40. And then the same thing again. Cost of theta cost of theta times 40 is equals to y. So just rearrange it like that. There you go. And then this, of course, is a negative. Of course, this shouldn't be y. It should be z because we're looking down from above. So there you go. That's an algorithm for calculating the initial starting x and z of all of the different particle effects. That's easy enough, isn't it? I guess it's just a matter of thinking about it like that. And immediately, you know, you've gone from having to hard code all these values and spend hours picking the absolute values, you know, and looking at them and trial and error, to a little bit of maths and a little equation, and all of a sudden you have this little particle effect that goes around in a circle like that. Cool. Right? Next thing I wanted to do is, does everybody understand that? Is that okay with everybody? So then it's just a matter of taking this little algorithm and writing it in C++ code. next thing I want to do, if you look at the particle effects here, right? Look at what the particle effects are doing. You know, they're kind of going up and down, but it's a nice, smooth up and down. It's not just, you know, going up as far as here and then changing the value and then going down and going back up again.
It's a burst and a drop.
Yeah. So there's loads of ways to do that. I could physically simulate it, but, you know, again, thinking about this, have you ever seen what a sine wave looks like? Has anyone ever just plotted a sine wave or tried it out? When you plot a sine wave or a cosine wave, what does it look like? It looks like this. So I'm going to use the same technique again to generate those undulating up and down things. Next thing. How do I get every second one to go up and every other one to go down?
The index in your form.
Yep. How do I know which ones go up and which ones go down? Huh? Modulus operator. Didn't you do the modulus operator in first year with Michael Collins? Hey, you can make these really cool effects with them now, right? So I just use, if it's modulus 2, I make it go up, otherwise it goes down. There you go. So it's every second one goes up and every other one goes down. So I'll show you the code for what that looks like. Okay, so here's what the code looks like, you know. So first of all, so I calculate the theta value. So I take 2 pi divided by the number of fountains. Okay, number of fountains is 20 or whatever it is, and then I multiply it by I, and then I goes from 0 as far as the number of fountains. That makes sense? So now I'm calculating the theta value. Create a fountain effect. Okay, 500 there indicates the number of particles you want in it. And then look at this, modulus operator. If it's modulus 2 equals to 0, I set the diffuse color equals to 100, which is red. Otherwise, I set the diffuse color equals to 0, 10. Red, green, and blue. Yep. And then I set the x equals to the sine of the fountain and multiply by the fountain radius. So you can see how that's that code there. And then the z is equals to minus the cosine multiplied by the fountain radius. And I set the y equals to the fountain height and I add them. So that's how I've created that ring of fountains around the outside. Does that make sense now to everybody? I guess, would you have known how to, or would you have had a crack at it if you had maybe a little bit longer to think about it? But would you know that that's now how you do those kind of effects? I'm going to show you a really nice one that I made during the week. Or actually, I just made it about an hour ago, whatever you do. I'm going to show it to you now. Here's the other thing, and this was slightly hacked together. I wanted the fountains to go up and down, so I want the y values to be affected by sine wave as well. So I created this other thing called fountain theta. This fountain theta value I set back to 0 again, right? And I just add the time delta to it. And then I just go and iterate through all of the fountains. Again, you know, checking the modulus is equals to 0. And then I set the y equals to the fountain height plus the sine of that multiplied by the fountain height. And then otherwise the y is equals to the fountain height minus the sine. So that's how I get some of them to go up and some of them to go down. And then I add time delta, and then I just check to see if I'm greater than 2 pi, I set fountain theta back to 0 again. So they're just sine waves, right? Here's the middle, and then I just add the sine wave to one, and I subtract the sine wave to the other, and then you get that lovely effect. What do you think? It's nice. Do you understand it now? This is the power and the magic of being able to sort of take a bit of game maths and apply it to solve all these beautiful things and make these beautiful effects, right? Yeah?
Why do you reset the fountain theta there?
Because fountain theta, I'm adding time delta all the time, but I actually only want it to go between 0 and 2 pi. So if it goes greater than 2 pi, I set it back to be 0 again. Because 2 pi is like one run through the whole 360 degrees, if you like. And then I set it back to 0, so I'm basically applying the same effect over and over again. You don't have to do that. Interestingly, if you don't have to do that and it just increases, it will still work. But you should reset it back to 0 again, because eventually you'll overflow the maximum value for a float. It might take several years to do that. regardless, this is the right way to do it. Reset it back to 0 again. You know what I mean? Because I wanted to go through one whole period, one whole 360 degrees, calculating the sine value, and then you'll notice that it's going to go up, down. That's one period. If you were doing digital audio, you'd learn all about frequencies and stuff, but that's basically called one period of a sine wave. If you plot one whole sine wave, you'll notice that it goes all the way up, starts there in the middle, goes all the way up, goes all the way down, comes back up. That's one period of a sine wave. You take sine of x, and you plot it, you'll get that. So that's what will happen if you make it go between 0 and 2 pi. So then once I start it back at 0 again, it will basically repeat the pattern. So that's called a period of a sine wave. It's just nice. You can do amazing things with just sine and cosine. Very first day of the class, like, we can already take that code and apply it to making magical and beautiful particle effects. Is that okay with everybody? Does anybody want to ask any questions about that? Or about the transforms or matrices and things? Alrighty, I'll tell you what. I, just for the hell of it, took this one step further. I was chatting to my friend Scott online there, and I had this amazing idea about sort of a trippy rift experience I could make using particle effects and sound effects and stuff like that. And this took me, I would say, all of about an hour and a half to code up, right? But if anyone wants to go with it, I have it running. I'm going to put it up on the rift here. I'm not even going to project it onto the screen here. You can just put it on and see what you think, right? Rihanna, you get to have the first go. And you know what we'll do in the second part of the class? We'll just play with this riff thing for about 10 minutes, and then I'll do the Git thing, and we'll talk about assignments, and we won't do quaternions until next week. Is that okay? So just let me check and see. I'm on the Buddha branch, right? So. Oh, sorry, I need to plug this thing out. I'll plug this thing in instead. You can probably, is the game controller, the game thing plugged in there, yeah? It's not what that thing is. The light is. Yeah, I mean, it's only a €2. I mean, do you mind stopping off the video there? Just hit the stop button and pause for a minute.